We're live. Cool. Hello, Sean. There was no countdown. Hey, what do you want to build today?
So today we are going to be building an adapter for an external protocol. In this case, we're building it for Curve 2 pool, which is a trading pool between USDT and USDC using Curve's stable swap algorithm. So one of the big innovations we're making with our upcoming iteration of Shell protocol is to make it backwards compatible with external protocols. So the purpose is to make it easy to migrate your positions through many different protocols, not just Shell. And adapters are how we do that at a smart contract level. And that's what we'll be looking at today.
Okay, cool. So we're going to build something that plugs Curve to some specific pool, you said, into the Shell ecosystem. Correct. So that it's therefore wired up to anything else that has an adapter.
Mm-hmm. Or even Shell native primitives like our own Proteus pools or anything like that. They're all composable with one another once this adapter is built.
Cool. So Shell protocol, you've got Shell. I've seen you have Ocean, you have Proteus. What is Shell? What is Ocean? What is Proteus before we get started?
So Shell is a composability solution. The problem that we see today in DeFi is that it's really fragmented, although there are these promises of it being like money Legos. In reality, when you want to do simple things, you kind of have to jump between a whole bunch of apps in order to execute your financial transactions. So Shell iterates on this and improves it by creating this central accounting hub called the Ocean. And what this Ocean does is that it stores all the tokens within it, and it's what handles all the accounting and shuffling of the tokens around. Then you can submit a list of instructions or interactions to the Ocean, and the Ocean will go through this list of instructions, query the appropriate primitives or pools that each instruction is associated with, keep all the balances in memory, and basically execute your long list of transactions step by step without wasting too much gas or having to jump around protocols and move tokens unnecessarily. So that's what the Ocean does. And Proteus is an example of a primitive that we've developed natively for the Ocean. And this is our AMM primitive that allows people to create liquidity pools, swap, deposit, and withdraw, and all that good stuff.
Okay, cool. So Proteus is like one example of something someone could build, but it's also one that's in production and people are using.
Correct.
Yeah, cool. And on the Ocean, then you talked about composability. The composability problems that we have in DeFi today are mostly because the protocols were built separately and not built to be interactive or interoperable. Sorry, and that leads to inconsistency of interfaces, having to wait for transactions to finish, and then of course you also waste gas because you're doing all this stuff in effectively separate transactions or separate processes, where if there were a unified system, which there is now with the Ocean, then everything can happen in memory. Like transient steps don't have to go out to different contracts and wait. Exactly. Is that the right way to think about it? Okay.
Yeah, exactly.
Good. So, and you said the upcoming release is focused on interoperability, which I guess, as one last question before we dig into the code, implies that previous releases sort of think of Ocean as its own ecosystem, where if you wanted to do DeFi or build DeFi in the Ocean, you have to look at the docs and build there, and all the liquidity would need to be there from the start, right?
Yep.
And that's not the case with what you're doing with adapters now?
So now you can think of it as an additive property. Of course, all the same things still apply, but now we also have the ability to integrate external protocols because their liquidity is not going to be in the Ocean, but we can still interact with them and create a standardized interface for interacting with them via an adapter.
Cool. And that's what we're going to do today with Balancer V2, you said?
With Curve.
Oh, Curve, sorry. Yeah. I don't know why I always get those words mixed up. Sorry, Balancer and Curve people. Cool. Well, let's get started then.
Okay. So I would start off by first looking at what Ocean adapters should look like. So we've already developed this template as an abstract contract, which any implementation of Ocean adapters should follow. So going over the variables here, first you need to know the Ocean's address because the adapter needs to know what the Ocean is. It also should make a record of the primitive's address. The primitive is the external protocol contract that you are integrating with. You also want to create a mapping of underlying token addresses to the corresponding Ocean ID. So let me talk about Ocean ID for a little bit. So Ocean ID is the Ocean's native way of figuring out what token is what. Instead of using the raw token addresses like for DAI or USDC, when you deposit your tokens into the Ocean, it generates a new Ocean ID for them. And this is generated via a one-way hash function that takes the contract address of the token, which is an ERC20 address or ERC721 or ERC1155, and it does the KEKAK 256 hash with the token ID. So for ERC20 tokens, there is no token ID, so we always do 0, and you can actually see it right here, the function implemented. So for ERC20, we don't have any token ID, so we do 0, but if it was a 721 or 1155 where you do have token IDs, then you do token address and token ID.
Right, meaning like NFTs that are non-fungible, they all have their own unique ID.
Exactly.
Right? Yeah, okay.
So the issue is that since this is a one-way hash function, there's no way to extract the original token address once you have the Ocean ID of a token. When that's where this mapping comes in, just so we can keep track of what maps to what. We also want to keep a track of decimals involved for each token, so we can figure out when it comes to unwrapping and wrapping tokens, how many decimals they operate with and the appropriate math to do there. So within the adapter, we also need to define our two functions that every Ocean primitive has, which is compute output amount and compute input amount. So these are the two functions that the Ocean will query as it's executing the list of interactions that you give it. So if you say, I want to trade through the Curve 2 pool, it's going to query this contract, specifically its compute output amount, to figure out how many tokens should I return based on how many tokens you've given me as the primitive. So it's computing the output amount that it should return. And similarly, you can do the same thing for compute input amount. You'll notice that this automatically reverts because we do not currently support this function on external primitives. The reason for this is because this function will assume that the Ocean has tokens to first give out to the user because it's working backwards. Instead of saying, hey, I have this many tokens, how many tokens can you give me back? It's saying, I want these many tokens back, how many tokens should I give you? However, the first step of giving those tokens to the user may not be possible based on the current Ocean's balances. So for external adapters, we do not implement this function, and we focus solely on compute output amount. Within compute output amount, we have 3 steps to it. So the first step is to unwrap the token. Since we are integrating with external protocols, we cannot just pass like a normal token to them. So when the tokens are in the Ocean, they first need to be unwrapped by the primitive or the adapter. Then you can call your external protocol to interact with it just as you would any other way. And then finally, once you get your output amount, you want to wrap that back into the Ocean and then continue on that way.
Can you drill into what wrapping and unwrapping means in this context?
Yeah, so wrapping is when a user deposits a token into the Ocean, and that's when the calculating Ocean ID function comes into play too. So this is just a way to get the token into the Ocean's ecosystem so that it's then it's able to be used with other tokens in the ecosystem, and then you can perform different queries with it. If the token is not in the Ocean, then you can't execute interactions on it because the Ocean assumes that all its tokens are within it.
Okay, so it's sort of like creating, wrapping it in a standard interface so that to the Ocean it just looks like a token. Every token is the same.
So every token, as far as the Ocean is concerned, is an ERC 1155 entry in its ledger.
Interesting. NFTs, everything, ERC20s, they all get wrapped as 1155s.
Yeah, exactly.
Interesting. Cool.
And then after this, then you can call the primitive output amount. And this is a function that each adapter has to implement itself. And this is where you actually make the calls to the external protocol you want to perform the swap, deposit, withdraw, whatever. So once you've done that and you figure out what the output amount is, then you simply wrap that value back into the Ocean and you're good to go.
Cool. So in the case of this curve two pool adapter thing, just popping up the stack a bit, what kind of thing would this allow someone to do once we're done with this that they wouldn't be able to do if it weren't part of the Ocean ecosystem?
So what this would allow people to do is to trade with the Curve 2 pool via the Ocean itself. And this allows for more composability in the sense that, let's say you had an LP position in the Curve LP pool and you wanted to migrate it to like a shell pool, for example. In the status quo, you would have to go to the Curve app, you'd have to withdraw your tokens, then go to the shell app and deposit again. But with this adapter, this can be done in one click via the shell interface itself. You simply select your Curve LP token on top, your shell LP token on the bottom, and it'll perform all the necessary steps in the middle to get you out of that pool and into the new pool. So this is where these smart contracts come into play to make it easier to migrate positions or just interact with protocols via the shell interface.
And with the composability of the Ocean, then if you had another similar system to Curve on like as an adapter, could you go end to end and do that migration through the Ocean?
Yep, exactly. So any pool that has an adapter built in the Ocean for it is then instantly composable with every other pool that is built on the Ocean. So because they all follow the same standardized interface of interacting with each other, it's very easy to move tokens around.
Yeah, your description makes it very clear what a pain DeFi currently is. If you want to interoperate between multiple systems, and also if you're saying that it will all happen in basically one transaction, right? Well, that's pretty amazing. Okay, I'll stop interrupting now and let's look at the code some more.
Yeah. So now that we've gotten into the Curve 2 pool adapter file, we can take a look at the variables here. So the three variables that we want to keep track of are X token, Y token, and LP token ID. And these refer to the Ocean IDs of the tokens that the Curve pool adapter has. So in the case of 2 pool, it operates between USDT and USDC. So the X token, it would be USDT, and the Y token would be USDC, or whichever ones the Curve pool uses. It could be backwards. And similarly, they also have an ERC20 token that represents their LP token of the pool, and we can compute its Ocean ID and store it in our LP token ID variable. So now let's get into the constructor. So the first thing that we want to do is figure out what tokens we're dealing with in the first place. And we can do this by querying the primitive itself. In fact, if you take a look at the interface of Curve 2 pool, you'll see that we have this function called coins. And coins is just their storage of basically which ERC20 addresses are in this pool. So you can either query it with coins 0 or coins 1 to get X token and Y token addresses, whether it's USDC or USDT. So if we look into implementing that, the first thing would be to grab the addresses. So let's get the X token address first. Then we want to call coins 0. One.
So these are the contract addresses of the actual tokens in the Curve pools, right?
And another thing is that once we have these addresses, then we have to convert them into Ocean IDs because that's what our primitive uses. It doesn't use the act. So we can initialize our variables like such. X token equal ID. And then token ID is 0 because this is an ERC20 contract, so there's no specific ID for it. Similarly, we want to store our findings in the underlying mapping that I was talking about earlier. So we have that. And then also we want to store the decimals of this token so we can perform the proper operations when it comes to wrapping and unwrapping. And we can use all right, and we can do the same things for
where did that metadata interface come from?
So this is a standard Open Zeppelin library that they provide.
Cool.
Just gives you details about ERC20 tokens.
So the decimals thing, is that so that you understand like the granularity, what's the right word in math? I'm so bad, but the granularity of the math that specific token uses?
Yeah, so for example, USDC and USDT both operate with 6 decimals, meaning that like 1 e to the 6 is equivalent to 1 for them. However, the Ocean operates under the assumption that every token uses 18 decimals. So this means that we have to do some arithmetic and like convert tokens to make sure that they play nice with the math rules that we are enforcing.
I see. And you chose 18 because it's a lot, and therefore because you have to deal with every possible token. You don't want to have an overflow where one uses more decimals than you can handle.
So we chose 18 because that's like the standard. Ethereum itself uses 18 decimals, and most ERC20s will use 18 decimals.
Mm-hmm.
There are a few tokens that use more, but we support them, but there will be some truncation going on to adjust for the precision issues. But yeah, 18 is the standard, so that's why we use it.
Precision is the word I was trying to find. Thank you.
Yeah. So we want to do the same thing for the LP token. To get the LP token information, we need to understand how the Curve contract works. Luckily, the Curve contract uses its contract as the ERC20 token as well. So the address of the primitive is the address of the LP token's ERC20 address. So that means that we can just compute the LP token ID by taking the primitive's address and hashing it with 0.
All right.
And similarly, we can pass its underlying because it is the contract itself. And its decimals can be found the same way.
Cool. This is all very simple. Basically 3 tokens having to map them to how the Ocean needs to deal with them.
Yep. Okay. And then the last thing that we need to do is, since these tokens are flowing into the adapter and then are going to be unwrapped out and wrapped back into the Ocean, this adapter needs to have permissions in order to do that in the form of token approvals. So you can see here, this approved token function has been written, and it basically approves a given ERC20 token address to be used by both the Ocean as well as the primitive. So it needs to be used by the primitive and the Ocean so that it can do its wrapping and unwrapping without fail.
You reminded me, I wanted to ask you, like, there's a bunch of code in this file already.
Mm-hmm.
Did you just fill in a bunch of boilerplates so you wouldn't be having to type it, or is there some generator? Okay, cool.
Yeah. I just wanted to focus on the meat of what we're coding today instead of writing.
Makes sense, yeah.
Yeah. So based on that, we should also be calling approved token for every token. Right. So that's our construction. Now we have initialized everything we need to start actually building out the logic for wrapping, unwrapping, and interacting with Curve 2 pool itself. So the first step is to figure out, let's start off with the primitive output amount, because that's the most important part. So in order to do this, first we need to figure out how many tokens we've gotten from the Ocean, and then figure out how many tokens we need to send to the Curve 2 pool itself, because the decimals are not going to align. When the Ocean gives us like a USDC balance, it's going to be in 18 decimals, but we need to unwrap it, convert it to 6 decimals, and then send it over to the Curve contract, because that's what it's expecting.
Mm-hmm.
So we can compute the raw input amount by calling our convert decimals function, which is given to us in our Ocean adapter file. So this handles the 3 cases of what a token's decimals could be. If the decimals are 18, or if the decimals are the same as what you want them to be, then you don't have to do any conversion and you can just keep the same amount. If the decimals that you're trying to convert to are more than what your current decimals are, then you kind of have to create some padding of zeros in order to bump it up to the appropriate number of decimals. Again, you have no truncated amount. But if the decimals are less, then you have to remove the zeros as well as keep in account how much was truncated as well. So this function will return both the converted amount as well as the truncated amount. And
Okay.
we can use it in our function here. So let's
By the way, I see you're working in this Shell Protocol V3 contracts project, I guess. Is that where an external person, like if I wanted to come try and build an adapter, would I clone this project and build it in here?
So this is an internal repository because this code hasn't been published yet. However, we do have public repositories that we can upload this later too. It's not going to have the same name, but yeah.
But you have repositories that have like all the structures set up, and,
Yeah.
and you just go add your adapter file to it.
Mhm.
Cool.
So what decimals do we want to convert from? So if we know that it's coming in as 18 decimals, which we've stored as normal decimals, actually. We just create a constant for it called normalized decimals because that's the standard. And we know that we want to convert to the appropriate amount of decimals for that token. Luckily, our decimals mapping will help us with that. So we're converting from normalized decimals to decimals of input token. And the amount to convert is whatever is being passed in here, which is input amount. Okay, now we have that. Now the next step is to figure out, the next step is to figure out what kind of interaction we are doing. So when the ocean interacts with any primitive, it basically just passes the input token and the output token, and it's up to the primitive or adapter to figure out what is this user trying to do given these two tokens. So if it's the X token and Y token, that means the user wants to do a swap. If it's the X token or Y token and LP token ID, that means the user wants to do a deposit. And vice versa, if the input token is the LP token ID and the output token is either X or Y token, that means that the user wants to do a withdrawal. So we've accounted for that in this determine compute type function right here, where it walks through those three scenarios and figures out what the appropriate compute type is. Yeah, this revert can just be just a revert because I don't have custom reverts. Does that make sense?
Yeah, it totally does. I'm amazed to say, as someone who doesn't do a bunch of DeFi stuff myself.
So we can call determine compute type on input token and output token, and this will tell us what type of action we're taking.
Is this from the Ocean adapter code, compute type?
This one was written specifically for this because when you have an Ocean adapter, it could be for anything. So it's hard, like it has to be on each primitive adapter level to figure out like what these different scenarios could be.
Right.
So it can be generalized. Yeah. One thing that I forgot to mention earlier is that we need another data structure when interacting with the curve 2 pool, and that's because we need to know what the indexes are. If you look at the interface of curve 2 pool, you'll see that when you want to exchange, you're passing I and J. You're not passing like token IDs. Instead, you're passing IDs that correspond to the indices of whatever's in the coin. So if you passed 0 and 1, that's a swap from X to Y. And if you pass 1 and 0, then that's a swap from Y to X. So we also need to keep track of what those look like. So we can create another data structure here called index of.
That's kind of a stressful, low-level thing to have to deal with in an API, isn't it?
Mm-hmm. Yeah. So then we can also store the indices in our constructor. So index of X. Zero. I need to do int 128. Solidity is very anal about getting your types right, so I got to make sure you do that. Cool. So now that we have index of, we can go on to actually using it. So let's just like load it in. And we're just doing it here because we're probably going to use it in multiple places, and we want to avoid invoking multiple loads when it's unnecessary. Cool. So now let's work through the different scenarios that we could have.
I normally don't feel like Solidity is a bad language, but whenever you're dealing with arrays and stuff like this, it makes me want TypeScript or something.
Yeah.
Although every language makes me want Haskell.
You should also create a placeholder variable for what the output will be, because we'll need to convert it later on. So we'll just leave it there. All right. So the first thing is swap. How do we do a swap? So within the curve tuple interface, we see that they give us this function called exchange, and this will reference how the curve tuple actually does a swap. So here we can just do it like this: raw output amount by curve tuple primitive exchange, and then I and j we found it via the index of the input token. And then dx is the input amount, but in this case it's raw input amount. And min dy is how curve does their slippage, so slippage protection rather. So whatever value you pass into this will then be enforced at the curve contract as the minimum output amount that this function should return. If you don't get that much, then you're going to revert. However, we implement slippage protection at our own level in the adapter, so which you'll see later. So in this case, we don't need to actually do slippage protection at the curve level since we enforce it ourselves.
Okay.
So we can just pass 0. Cool. And that's
remind me what primitive is here on this line.
Primitive is the address of the curve tuple. So we're basically making a call to the curve tuple's contract saying, hey, we want to exchange these 2 tokens with a raw input amount. Oh, yeah.
Cool.
Yeah. And then it will return however much we got back. So that's actually it for doing a swap. That's the only line of code. Like that'll call the curve contract, perform the swap on their contract, and return the appropriate tokens and amount as a result of the function call. Now let's take a look at deposit. So deposit uses a different function. It uses add liquidity, and this takes in it takes in an array of 2 referencing the amounts of deposit for X and Y token. And it also takes in mint amount, which is the minimum number of LP tokens you want to be minted as a result of your deposit. The thing is that since our adapters and our primitives only support one step at a time, meaning that you can't do a dual-sided deposit of both X and Y token into the LP token in a single go. You would have to do it piece by piece. So first X token deposit and then Y token deposit, because the primitive only interacts with 2 tokens at one time, never 3. So based on that, the workaround here is just to pass 0 as one of the amounts and fill in the amount of the token that you actually want to deposit into the pool. So we can figure this out by first creating a data structure called input amount of memory. And then we can initialize the appropriate.
So here you're working around a limitation in the internal interfaces of the Ocean adapter stuff, which I assume is a limitation because you have to design it generically to deal with all different systems.
Yeah.
Yeah, makes sense.
So here we have this because, yeah, should be index of, oh, sorry, index of input tokens. So here we can specify, because we know the index is either 0 or 1 for the input token, and we have to convert it to the appropriate type by first doing int256, then to uint256, so that we can initialize the appropriate value in input amounts to our raw input amount. And then finally, we can just call the same function. Once again, since slippage is being enforced at our level, we can just pass 0 because we don't care how many curve gives back to us. And that's it for deposits as well. So now the last one is withdrawals. And if we go back here, luckily for withdrawals, it makes it much easier because we only have to pass in the amount of LP tokens we're withdrawing and the index of the token that we want to withdraw into, whether it's 0 or 1 corresponding to the Y token. So this one can also be done in one line where you just get raw output amount
So I have a really stupid question for you on this one, which is pretty fundamental, I think, to the whole adapter. When you remove liquidity through this contract, does that then reassign it to the address of the person interacting with it? Does that question make sense?
What's happening here is when the user wants to withdraw liquidity, first they are passing over their LP token to the primitive. Then the primitive will withdraw the liquidity on their behalf. So whatever like resulting token of the withdrawal is going to be in the primitive's possession or the adapter's possession. Okay. Then once the adapter has it in its possession, it can wrap it back into the ocean and then say, okay, this is how much the user is going to get because this is how much I got.
So if I were a user just directly calling this curve contract, it would put the tokens back in my possession as the user. Yeah, okay. Makes sense. Thanks.
So now we've accounted for the 3 different scenarios of computing raw output amount. So now we want to convert this to the appropriate values based on, again, the ocean uses 18 decimals, so we need to account for that. So now we can assign our output amount variable. Then
and again, here the second return value would be the truncation amount, which doesn't mean anything here.
Yep, exactly. And now here's where we can enforce our own slippage protection, where we do if uint256 output amount is, uint256 minimum output amount, which you can see here because the user will pass into the adapter like their slippage parameter, which is how much minimum output they want. And if that is greater than whatever we've computed, then we have a problem and we want to revert.
Greater?
Yeah, because if this means that like the user specified, hey, I want at least this many tokens, and if we find that we can't give them this many tokens.
Oh, right. Yep. Okay, thanks. Some days I don't speak my mother tongue very well.
So yeah, that's our slippage protection function, and that's pretty much it in terms of doing the actual calling to the curve contract. Are there any questions so far about this function?
No, this is totally clear.
Cool. So the next step is to implement the wraps and unwraps. So if you see in the Ocean adapter code, before we call primitive output amount, first we need to handle the unwrapping and the wrapping of the token. You'll notice here that unwrapped token actually produces a return value whereas wrap token does not. And the reason for this is to account for potential decimal truncation. So for example, let's say that you pass a value of USDC, which is 6 decimals, but since it's in the Ocean format, it's in 18 decimals. And if you invoke it with more precision and when it's in its 18 decimal format, then when it comes time to unwrap, then there will be some loss of precision because you're not getting as the entire 18 decimal section.
Mm-hmm.
So unwrap token, we've delegated to be responsible for handling this edge case and figure out what is the appropriate amount to actually return back as the value. So we can start off with unwrap token. So the first thing to do is figure out what is the address of this token, and we can use this doing our underlying mapping that we created earlier. This gives us the ERC20 address of the token we want to do. And now we're going to create an interaction which we're going to submit to the Ocean to actually perform the unwrapping. So we'll do interaction. All right. So the anatomy of an interaction is that there are 5 fields to it. There's interaction type and address. There's input token, output token, specified amount, and metadata. So let's just go through that.
And this is an Ocean structure, this
Yep.
interaction thing. Yeah.
So this basically just encodes the data of what type of interaction we're doing here. So we've specified that we want to do an unwrap ERC20 of this given token address. Oh, it should be token address. Next thing, input token 0. So for wrap and unwrap interactions, we don't need to specify what the output token and input token are because that data is already encoded in the interaction type and address. We already know what address and what we're trying to do to it. So we don't need to know the input token and output token. We do need to know how much we want to unwrap, which is just simply the amount. And metadata doesn't need to be passed because this is just an unwrapped price.
Okay.
Now that we've built our interaction, it's time to actually execute upon it, which we can do by calling the Ocean. So this will actually make the function call to the Ocean with this interaction step, and the Ocean will execute it on it for us.
So what you're doing here is basically executing some function in the Ocean, but you're doing it through this abstraction. Is that so that you can do things like queue up a bunch of these and run them all in one step, or why not just call a function?
Which function are you referencing when you say call the function?
Well, like this whole interaction could be a function call somewhere, right? Like you're just doing one thing.
Mm-hmm.
So why is it not a function call versus creating this structure that's generic and then calling do interaction with it?
So the reason that it's based on whatever adapter you're building. So for example, let's say you're building an adapter for like a token fractionalizer where you can take an ERC721 and convert it to an ERC20 fungible equivalent, right? So based on those different scenarios, the implementation of wrap and unwrap could be different. Mm-hmm. And yeah, it's based on the adapter level, like how it wants to implement it. So this is just the standardized way of doing an unwrap through the Ocean, but different adapters may not use this code. So that's why we implemented it like this.
Okay. Yeah, I guess I was more asking what the purpose of interactions is generally. versus some other mechanism that's just like synchronously calling a function somewhere?
Oh, so well, this is just an example of doing one interaction. If you had multiple interactions, you could create an array of interactions and pass that to the ocean as well. So because we only need to do one, we only pass one.
Okay, makes sense. It is like the whole optimization step of being able to run multiple things in one transaction versus calling the contract over and over again. Okay, cool.
Yeah. So now that we have that, then we need to handle a scenario in unwrapping tokens. So the way that the ocean is supposed to generate revenue is by taking a small fee on every time an ERC20 token is unwrapped from it. The problem is that because this fee could exist, then we need to account for it when we're unwrapping tokens before interacting with external protocols. So here we handle that scenario. So the reason why we do it like this is because the ocean stores its unwrapped fee as a divisor. So that way it can figure out what exactly it needs to do. If we look at here, so here we can see that the fee charged is based on this divisor where you simply just divide it by however much you're unwrapping, and that'll get you like the fee that you're being charged as a result. Cool. So once we have this, then so here we're accounting for the fact that some unwrapped fee has been taken from us when we unwrapped our token, and we want to make sure that we convert it to whatever decimals we want for the token, whether it be 6, 18, whatever it is. And then we have the truncated amount because, once again, we could be passing too much precision and we're whittling it down, but we want to make sure we keep in mind how much we lost. So then we can re-account for that here. So then your unwrapped amount is, sorry, first you have unwrapped fee equals unwrapped fee plus truncated. And then your unwrapped amount is simply however much you wanted to unwrap minus the fee that was taken.
Right. And the ocean has already, or will have already, charged the fee. You're not responsible in the adapter for doing that, right?
Yeah. Yep, exactly. All right. So that is your unwrap function. And now we can do, it's much easier for wrap, actually. It's literally just take this guy. Boom. That's it. That's your wrap function. Very easy. No need to account for any wrap fee or anything like that. So that's that. Cool. I think that is everything in terms of what the adapter needs to do. So now I guess we can test it. So I've already written a test file, which we can go over here. This goes through the different scenarios. We can go over the variables first. First, we just found a dummy wallet that has a bunch of USDC and USDT, so we can execute trades on their behalf and simulate. We also found a wallet that has a bunch of LP tokens of this pool, so we can simulate withdrawing from it. And then here we just keep track of the 2 token addresses, USDC and USDT. We're able to basically fork the current production environment of Arbitrum in order to run our test to make sure it works appropriately. And then we want to VM.prank wallet basically assumes that this whatever next line is being done on the behalf of wallet. So this allows you to simulate doing transactions with whatever wallet you please. The first thing is to deploy a new ocean to the production environment simulation, and then we want to deploy our adapter contract. This address is the address of curve tuple on Arbitrum. So we're just basically saying, hey, make my adapter for this primitive.
And everything we're doing is on Arbitrum here, right?
Exactly. Yeah. All right. So the first scenario we want to do is testing a swap. We also want to simulate it with a variety of unwrapped fees as well. So this bound function basically says, okay, actually, before I get into that, we should talk about how these tests work. So these are fuzzing tests, meaning that the computer will try out a bunch of different values for the 3 input parameters you have, and it'll see if it can break it given any like combination of these parameters.
Right.
You can invoke your own restrictions on it via like such as bound. So if you don't want there to pass any value for unwrapped fee, you can bound it to at a max of 2,000, for example, because that's the max we want. And then we call change unwrapped fee just to set the ocean to have that unwrapped fee. And now into the actual swap logic, where we have the toggle variable can let us simulate both swapping x to y or y to x based on whatever value is passed there. And we also want to bound the amount based on however many tokens the address that we're simulating with actually has. We can't simulate a swap with 1,000,000 USDC if the wallet only has 100K, right? So we do that. And we also want to approve the token, and we want to keep track of our invariants that we're going to be asserting later on to make sure the swap went through as planned. And this is where you can see an example of what we were talking about earlier of like submitting a list of interactions to the ocean. So you'll see on a user's behalf, what they're doing is first they need to wrap their token in with this wrap ERC20 interaction. Then they want to call compute output amount on our adapter. So you'll see that the fetch interaction ID, you pass the adapter, and you pass compute output amount. So this next step is saying, hey, hit up the adapter contract and ask it to run its compute output amount function and see what you get. You'll see that the specified amount is type uint1256 max. And what this is it basically does a flush of whatever's in the memory for that token's balances at this point in time. So after the first interaction, when you wrap your token, it's going to update its memory with however many wrap tokens you have earned as a result of your wrap. And then this next step will take whatever value is stored there and pass it on to this next step there. And
Great.
Similarly, you do the same thing when you want to unwrap your token at the very end. It basically passes whatever the output amount was of this and stored in memory. You want to completely flush it out and unwrap it, and you do that via calling max.
It makes sense. Simple.
Mm-hmm. So then you also need to create an array of the IDs involved in all of these steps. So since we only have 2 IDs, it can be of length 2, where it's just the input address and the output address. And again, we're calculating Ocean ID, which does the same kekak hash that I pointed out earlier. I've hard-coded it to be 0 here because I know in this test file we're only interacting with the ERC20 tokens, so we can make sure that that works as planned. So once you have built all that, then you simply just call ocean.do multiple interactions, and this will send your list of interactions to the ocean, and the ocean will execute upon them for you. Then finally, we can take a look at our new input balance and new output balance, and we can run assert statements to make sure that it works as intended. We should have less input now because we gave it up in the swap, and we should have more output now because that's what we gained during the swap.
Mm-hmm. So for this fuzzing thing, is there something that like runs this in a loop for you? Is that how it works?
Yeah.
Okay.
So we use Foundry, and they have inbuilt fuzzing tools. So you just have to run forge test, and it'll run it for you. And you can even like configure the amount of runs you want it to do. So if you increase, which one is it? Yeah, fuzz here. If you increase this value, then it'll just fuzz it with more.
Oh, wow.
Yeah.
That's a great feature to be built in for blockchain development, especially.
Yeah. So yeah, that's how the fuzzing works. Okay, back here. So we have similar concept when it comes to test deposit as well. We only need to specify the input address. It's either the X token or the Y token, which is USDC or USDT. And the same concept will apply. We know that our output address is going to be the LP token, which is the same as the primitives address. So yeah, the same concepts apply. You build your step 3 list of interactions, wrap, execute, like wrap, compute output amount, unwrap, pass the appropriate IDs, and then same thing. You can do that. And then similar concept for withdraw. You need to pass your input ID being the LP token address. Output ID is either X token or Y token. Build your set of 3 interactions, execute them, make sure the values line up. Pretty simple.
Yeah, great.
Okay, so now let's take a look at this. So we can do forge build.
So you really could have built this in a couple of hours from scratch.
Yeah.
Nice.
So that's our goal. Like we want to make it as easy for people to build these adapters so that they can like execute on them on our behalf and we can just integrate them. Okay, cool. So we passed. We just have a few warnings. Let's see if this works. Test.
This whole fuzzing thing is all happening in memory, right?
Yeah.
Yeah.
Yeah, great. And now we're passing all our tests.
Cool. So
yeah, that's a pretty good look at what an adapter should look like, how to build one, what the different components of it are. Do you have any further questions?
I do, yeah, just higher level stuff. Then once you've built this, like let's say I wanted to come along and contribute something as a developer that just watched this video.
Mm-hmm.
I guess you said there's a public repo that I would maybe do a pull request to. Is that how I do it?
Yeah. We actually just got this code audited recently, so we're like working through the kinks that we received from that audit, and then we're going to publicize it afterwards. So it's not up just yet, but it will be soon.
Yeah, I ask mostly because I'm just trying to make sure I understand, and that whoever watches will understand the whole process. So you would add this; it would be basically an official adapter that's part of Shell, right? Mm-hmm. And therefore, to deploy it, I wouldn't need to know how to deploy it because the Shell team would deploy it, right?
Yeah.
Okay, cool. And then what does it enable immediately from an end user perspective? So like you have this UI that's very flexible for DeFi, where you can do like swapping NFTs for ERC20s and all this sort of thing. Will you update the UI as you add adapters, or will it just automatically plug in, or just making it concrete?
So currently it's like we have to update the UI ourselves in order to like account for the new adapters and what tokens they're integrating. Mm-hmm. In the future, we hope to build it so that it's much more like automated, whereas like the UI can detect that someone deployed an adapter and it can figure out the appropriate details for it and load in the token details into the UI directly. But currently it's the team has to manually integrate them ourselves.
Cool. I mean, the good news about that is if I'm a third-party developer, my work is very simple and very contained. Like make an adapter that conforms to an interface and write some tests. And if they pass, and I believe the logic is correct, then I submit it. You guys look at it and decide whether to integrate it. You do, and then I'm done.
Yeah.
And now we've got this lovely connected ecosystem.
Yep.
Is there any other project that creates this kind of composability through all these DeFi systems?
So there are other projects, like one example is like Instadap or DeFi Saver. I think the difference is that they don't have like a centralized interface for like building these adapters. And when they build like connections between various DeFi protocols, it's kind of each time they're like restarting from scratch, or like it's not a hub and spoke architecture where you have one central guy and you can like everything looks the same to it. It's more so like, no, we've built very specific pipelines to integrate different protocols. So that means that when it comes time to integrating a new protocol, you probably have to do more work to get it backwards compatible with everything that came before it. But that's not the case for Shell. Once a primitive is deployed here, it's instantly composable with everything else that came before it and will come after it because they all follow the same interface.
Cool. Cool. So where should people follow along to see like when this new repo is up and various other announcements?
So I would say our Discord and Twitter are the best 2 places to keep up to date with Shell information. Especially Discord is where some of the stuff like the alpha gets leaked, But yes. This code is scheduled to go into production in January, along with our TGE, which is slated for January 22nd. So yeah, there will be a lot more information the closer we get to that date.
All right, excellent. Well, thank you so much. This was a lot of fun. I feel like I finally get it after like reading docs and talking to you guys. It's always better for me to see things concretely like this. And thanks for a really great explanation too.
Yeah, no, it was great. It was fun working through it.
All right.